Hi everyone, sorry my phone went off halfway through that explanation, but since I'd taken the trouble to record and explain that much, I just let it be. So this is continuation and we are looking at this part of this question of your assignment. And so the deck of the boat is at high tide and we need to know how far does it drop 1 hour after 11 o'clock. Okay. So in order to do this, and we had to mark position B, which was low tide. So position B is going to be at the bottom. And position C is where's the deck going to be 1 hour after high tide. So 1 hour, so high tide is at 11 o'clock and noon is 1 hour. So it'll be somewhere here because it takes 3 hours to go from there to there. So 1 hour, it'll just go a little bit. Okay, so I've drawn it here. Okay, so assume that's position C. So we need to figure out what's this angle. So your phasor has gone from there to here. So the first thing we have to do is figure out what angle does it move through. So in order to figure out what angle it moves through, we use our knowledge of the period. So the period is 12 hours. So in 12 hours, it moves 360 degrees. So how many degrees would it move in 1 hour? So I just use a proportion. So 1 over 12 times 360, you get 30 degrees. So this angle is 30 degrees. And then what we're going to do is we're going to convert this to a right angle triangle. If we can calculate the displacement, if you know this distance, this is the one that's required from A to C. So 2.3 minus that distance will give us that. So in order to get y, so this is adjacent and that's the hypotenuse. So we're going to use cos theta. Cos 30 is y over 2.3 or y is equal to 2.3 cos 30. And that works out to 1.99 meters. So the distance from A is 2.3 minus 1.99, which is 0.31 meters. So that's how you get that. And then there was a question saying calculate angular frequency in radians per hour. So angular frequency is 2 pi over t, so which is 2 pi over 12. You put that in your calculator and you get the angle. Sorry, it's got rubbed off. As 0.524 radians per hour. Okay, and then there was a question about the very last one. So a few people asked me this one. So here we just read the question and I'll explain that last part. So a passenger is standing on the deck of the boat and whoever is standing will have two forces acting on her. One is gravity force that acts downwards and reaction of the deck she's standing on. Then by considering the size and direction of the unbalanced force acting on the passenger, explain how the size of the reaction force changes as the tide drops from high to low. So here we go. This is how I'm going to explain it. So I've drawn the reference circle. Where's my blue pen? Okay, oh, I've got the red. Okay, so on the reference circle, just trying to open this red pen. Oops, I can't. Okay, I'll just explain, talk you through. Okay. It's hard holding the phone in one hand and trying the pen in the other hand, but never mind. Okay, so this is at equilibrium position, and you know in simple harmonic motion at equilibrium, the forces are balanced. There is no unbalanced force. So the size of the gravity force will be the same as that of the reaction force because the difference between the two is 0. Okay, and that's what happens at equilibrium position. Now that's a position at high tide, that's a position at low tide. No matter whether it's at high tide or low tide, the size of the gravity force does not change, it stays the same the whole time. What does change is the size of the reaction force depending on which way is the unbalanced force acting. And yes, so the thing is, no matter whether this thing is moving up or moving down, your unbalanced force will always act towards equilibrium. That's your restoring force, okay? And that's where the acceleration and restoring force always towards equilibrium. So when it's at the top of the motion, your unbalanced force is downwards. So if the unbalanced force is downwards, your reaction force is always acting upwards. So your reaction force will have to be really small because the leftover force, unbalanced force, has to point down. So at high tide, the reaction force is really small. So the length of that arrow will be just a tiny little red arrow, if you can imagine. This pen doesn't write on this white thing. Okay, Let's go all the way down. When it's down, your unbalanced force is still pointing towards equilibrium, okay? Whether the thing is moving up or whether the thing is moving down, okay? So if it's pointing towards equilibrium, the arrow that's pointing upwards has to be bigger, because the difference between the two has to be pointing upwards. So that means your reaction force is bigger than gravity force. So if you're comparing the size of the red arrows, which represents the reaction force, it's smallest over here, gets bigger, and very big at the bottom. So what's happening to the size of the reaction force? It's getting larger as you go from high tide to low tide. I'm just going one more step. I know they haven't asked you in this question, but suppose the question was framed differently and asked, what is the feeling of weight for a passenger who is going up and down in simple harmonic motion? Now, the feeling of weight depends on the size of the reaction force. So when the reaction force is the same as gravity, you feel normal. But if the reaction force is smaller than your gravity force, you're going to feel lighter. At the bottom, when the reaction force is very large, you're going to feel really heavy. Okay, so I hope that made sense, and bye for now.